Right. Let's go ahead and get started for our next presentation. So I would like to welcome up Dr. Vernon here, who's going to be speaking about how Ceph is being used in genetics research. Kick it off.
Have you ever thought about deletion at scale? You come to sessions like this and we talk about how easy it is to scale up your storage, scale out your storage, what sort of speeds you can get. But have you ever thought about deleting at scale? We had someone come to us and say, I've got 70 million objects in an S3 bucket occupying a bit over a petabyte. I want it deleted. That turned out to be not entirely straightforward. I'll start with some background before I come back to that, though. I should say, if you have questions, do wave. There will hopefully be time at the end, but if you're confused, probably I've missed something important, so do wave and interrupt me, and I'll take questions as we go. I work at the Wellcome Sanger Institute. This is a picture of the campus. We're just outside Cambridge in the UK, and we're a leading centre of genomic research and gene sequencing. We are the largest single contributor to sequencing the human genome, and we continue to sequence more than just about anybody else. That means we have a lot of data. I know you can't really come to CERN and say you have a lot of data, but we have quite a bit of data. We have about 50 petabytes on campus at the moment. And for a long time, our compute has been based on batch computing, so LSF clusters, and we still have about 20,000 cores in our LSF-based clusters, and we provide storage, fast scratch storage for those via Lustre. A few years ago, though, we decided we should start looking at OpenStack to provide a more flexible compute environment for our scientists, not only so that they can use pipelines developed elsewhere, but to give them more flexibility about which operating system distribution they're using, and also to enable them to produce standardized pipelines they can then share with other people. If you're working in a batch-based compute environment, inevitably your pipelines are going to be specialized to that particular distribution, the file systems available and such like. Whereas in OpenStack, you can have containerized pipelines that you can then share with other people. And when we started down that road, we didn't really know anything about Ceph, but it was still the obvious choice to provide storage for OpenStack, essentially because it's what everyone else uses. And when we started with Ceph, we noticed the RGW facility and thought that might be useful, so we turned it on almost as an experiment to see what our users thought of it. And it turned out to be wildly popular. At one point, over 90% of our Ceph storage was actually backing the Rados Gateway, the S3 service, rather than OpenStack itself. And when I gave a talk at the Ceph conference in Barcelona this year, it seemed that we were unusual amongst scientific institutes in the amount of S3 we were using. So I thought today I would talk a little bit more about our S3 service and some of the good and less good points we've had with it. In case you like a picture of hardware, this is the hardware we base our Ceph clusters on. These are 4U servers. If you can count quickly, you'll see the 60 disk bays there. In our setup, those are 6 terabyte drives. And then we have some NVMe for BlockDB for BlueStore and twin 100 gig networking, which we bond together. Give you an idea of the sort of timescales we're talking about here. We first started using Ceph in 2016. Our first deployment was 3 servers in the bottom of 3 racks, the rest of which were filled with the OpenStack compute, and that gave us 3 petabytes of raw capacity, equating to about a petabyte of usable capacity. We used 3-way replication, essentially because we didn't know what we were doing and it was easy, and we've continued largely using that because it's easy to understand, easy to look after. Ceph proved popular, both in terms of OpenStack and specifically the S3 service, so we expanded relatively rapidly in 2017. We filled those 3 racks to 14 nodes each, and then towards the end of 2017, we added a 4th rack of 9 nodes, bringing us to a capacity of just over 18 petabytes in our main cluster. That 4th rack came as its own failure domain, its own cabinet, and from it arriving on site to being deployed and in the cluster and available took about 4 days. And if you compare that with the time it takes to commission similar size file systems for, say, Lustre, that's pretty attractive. In 2018, we added a test cluster, which was particularly useful when we were migrating from Joule to Luminous and from Ubuntu 16.04 to Ubuntu 18.04. We found some unfortunate bugs in terms of SSL library versions, which in our test cluster would find and would be a bit embarrassing in production. Similarly, we now have a disaster recovery site in Slough, just outside London, and we have another small cluster there. So we now have 3 clusters, and we're looking to get a 4th soon to support some work we're doing for the UK Biobank, which is going to be sequencing another 500,000 human genomes. We manage our clusters using Ceph Ansible. If I have a quick show of hands, who here is at least somewhat familiar with Ansible? Pretty much everyone, good. That means I don't need to spend much time on it. Essentially, Ansible is an idempotent configuration management system, and it's agentless. So nothing is running on your target machines. Instead, you have a controller which logs onto machine to make sure their configuration on those targets is as you've specified. And Ceph Ansible is a series of Ansible roles for the particular things you would care about in a Ceph cluster. So the monitors, the managers, the OSDs, the Rados gateways. When we started with Ceph Ansible, it was still very much in development, and now it's settled down into releases, which is, and we are using a branch off the latest release. And that branch has some of our bug fixes that haven't quite made it upstream yet, and also our local configurations. So we set up our bonded networking and all that sort of thing. And we have some local management tweaks as well. So we have a script that manages failing OSDs, and that's for our data center team. The output of this script includes things they need to know for replacing the drive, smart errors, it's the serial number of the drive, and a little ASCII map that shows them which drive to pull, as well as lighting up that drive. And that's been quite helpful in that our data center team don't have to know much about Ceph. They just know which drive needs replacing, and that means I have to spend less time in the data center, which is great. The other thing we've done is for our Rados gateway, we use Let's Encrypt, which is a free TLS certificate authority that produces very short-lived certificates. They last for 90 days. So essentially, you have to automate your deployment. And we have some scripts that do that, and they distribute the keys between the Rados gateways using Rados itself. If either of those things sound interesting, the last slide has links to them. They're on GitHub. You can use them yourself. So I thought I would talk a little bit more about the Rados gateway, which provides S3, Amazon's simple storage service. We initially set this up thinking that our scientists might want to use this to share data with each other. Our institute is very international. We have a lot of collaboration with institutes across the world. And indeed, that turned out to be very popular, both in terms of simply providing a secure way to share data. You don't have to give someone else an entire credential. You can send them a signed URL, and then they can download either just a single object or the contents of an entire bucket securely over HTTPS. And as has been mentioned previously, essentially this gives you object storage over HTTPS. So you have buckets into which you put objects. Perhaps inevitably, though, our scientists look for more creative things they could do with this. And some of the services we provide is analyzing other people's data. And that used to be a case of literally shipping hard drives around, which had all sorts of problems, particularly rather than sending us anonymized samples, we would tend to get the full details of study participants, which under GDPR is a bit unfortunate. So now we have a number of teams have set up web front ends where their customers can essentially upload a manifest of which files they want to upload, and it can check the contents are right on the client end before securely uploading those to S3. And this has been good for our scientists because it means we're not dealing with disks anymore, and I think it's provided a good experience for their customers as well. Scientists, though, do other things, and as I said previously, we used to work a lot with batch computing, and that meant people had access to fast scratch file systems from Lustre. You can't straightforwardly give access to Lustre from OpenStack because people's machines in OpenStack, they have root on. That would give them root on the Lustre file system, and that's no good. We do now have ways of securely giving Lustre to OpenStack, but they're still a bit fiddly to set up. So people started using S3 essentially as a way of sharing state between their compute jobs, which is fine in and of itself, but they then noticed that some clients would let them essentially mount an ersatz file system on top of S3. So rather than using it as an object store, they were trying to implement a POSIX file system on top of that, and that started to cause problems. This is some output from our monitoring service. It looks like you can just about make out those lines. The top graph there is the number of open S3 connections by IP address, and that pink line is one IP address holding open all of the connections. Civet Web, which is the part of the Rados gateway service that provides the HTTPS front end, has a fixed number of threads. You can configure it, but once you've configured it, it stays fixed. And that means those gateways can provide a fixed number of HTTP connections. And what we were starting to see was that someone would spin up a cluster, its cluster would decide to try and mount S3 like a file system, and essentially their nodes would open a bunch of HTTPS connections, do a bunch of transactions, and just hold them open indefinitely. If you look at the bottom graph, this is requests per second by an IP address. This is the same IP address as in the top graph, and you can see actually while it's got all these connections open the entire time, it's not making heavy use of them. The effect of this is we would have people coming to complain to us that they couldn't get through to the Rados Gateway service, and we'd look at it and see it wasn't actually shifting much data, and this was directly due to this problem of clients holding open connections indefinitely. Also, we'd see that essentially you can perform a denial of service attack. We started off with 3 Rados Gateway machines, and we now have 16,000 cores of OpenStack. And you don't have to be particularly creative with 16,000 cores of OpenStack to be able to knock over 3 Rados Gateways. And we first worked around this by starting to add Rados Gateways for particular services. So our CI system needs access to S3 to store its build artifacts in. So we gave it its own dedicated Rados Gateway, but that solution obviously doesn't scale very well. Also, we've got some dedicated hardware coming to provide Rados Gateway service, and that will mean we can tune those more aggressively because at the moment our Rados Gateways are just machines running OSDs in the same way that our monitors are machines running OSDs. So we have to be careful that we don't overwhelm the OSDs in the same box. So once we have these dedicated Rados Gateways, we'll hopefully get more performance out of it, but we still have to do something to stop either single machines hammering the entire service or hogging it by keeping it, connections open. So we've added HAProxy. If you're not familiar with HAProxy, it's a bit of free software that provides caching and proxying services, and it also gives us some of those sort of tuning that you would like in a web server that Civet Web doesn't provide. So we really set that to do 3 things. One is it provides a hard limit on connections per IP address. So if you've got, say, 400 connections, you ask for another one, it'll just say no. There's also a softer limit it can provide whereby above that lower level, you can still get more connections, but if anyone else wants a connection, they'll get in before you. These 2 things mean that no one machine in the cluster or set of machines in the cluster coming through NAT on one address can hog the entire service. The other thing we can do with HAProxy is stop people hogging idle connections. And we don't just do that by saying at the end of HTTP, every HTTP transaction will kill the connection, because pipelining is quite useful. It's a big efficiency saving, especially when you're doing HTTPS. There is some overhead to setting up a new TLS connection. So instead what we do is we say you have a little grace period, currently a second, between one HTTP request and the next, and if you don't use it, then we'll close the connection on you. And the effect of that means that our graphs now look rather more like this. The top graph, again, is open connections by IP address. And you can see those sort of peaks and troughs there as the client downloads some more data. It tries to hold all of its connections open, but HAProxy says, well, these connections are idle. We're going to disconnect them. And S3 clients handle that sort of thing transparently. So the users don't notice that you can't keep their connections open all the time. But what you can see now in the bottom graph, there's not just one set of peaks, there's some smaller peaks as well. And what that's showing is that everybody else is still having access to our service, even when somebody is using it quite intensively. So that's really helped in terms of the overall reliability of the service. And we're also hoping that once we've got some dedicated machines as well, we'll be able to see much higher throughput. I said I would return to that problem of the large bucket. If you're familiar with the Rados Gateway, you'll know there's a command Rados Gateway admin that has all sorts of useful functions in it and a whole pile of options which may or may not be documented. And it has a bucket removal option. You can tell it to bypass garbage collection. You can parallelize lots of I/O. But we still found that we would run this on this very large bucket. It would run for a day or two and then fall over in a heap. There were 2 particular problems. As objects get put into S3, they're split up if they're large, and you end up with a bunch of shadow objects, which are, if you like, bits of the object that was inserted, and then a head object, which is written last and deleted last, that says things like how many shadow objects there are. So the deletion command would come along to a new object in the bucket. It would start deleting those shadow objects, and then it would find one that had been partially deleted from some previous failed deletion run and go, rather than saying, well, I'm deleting this object, who cares if something's missing, it would stop and fail. Similarly, if you've got part-deleted buckets, you may find there are objects in the index, so there are OMAP entries, that no longer correspond to objects in the bucket. So again, when deleting a bucket, the bucket removal command would get to these, and rather than saying, well, I'm deleting it, I don't mind, would fail. So we went round and round having to sort of manually fish these things out, and the whole process took about 3 weeks. Those underlying bugs have now been fixed. Our support vendor, Canonical, have put patches into master, and they should be backported into Luminous too. I guess sort of the point here is that our Rails Gateway service was a bit of the victim of its own success. People realized how useful it was and then started doing all sorts of things we'd never really envisaged, and we didn't quite keep up in terms of provisioning more Rails Gateways and looking at how the service performs with very large buckets. I think there's still operations with large buckets in terms of number of objects can be problematic. Even with resharding, which helps, anything that involves listing the bucket, which deletion will do, takes quite a long time. I don't really want to end on quite such a sour note. For all, we've had some issues with the Rails Gateway. Ceph itself has been great, both from our point of view and our users' point of view. It's very reliable, scaling it out is straightforward and quick, and it's dealt with hardware failure much more gracefully than in the other file systems we have. I'm about out of time, and I don't want to make us any later, but I think we've probably time for a question or two if anyone's got one. No? Okay, thank you.